A series of lectures by Professor George Phillies, based on his book, Phenomenology of Polymer Solution Dynamics, Cambridge University Press, 2011. And stand by for our forthcoming lecture series, Statistical Mechanics, Introduction to Mechanics, Harmonic Oscillation, and Game Design. The following measurements and the associated discussion are an extremely small sampling of results from figures in my book. These lectures only sketch what is in the book. If you want to see my real results, you need to read it. Lecture 6, Electrophoresis, based on my book, Chapter 3. Recently, new physical methods have been applied to study electrophoretic motion of polymers through matrices. These results, due to workers such as Carlson et al., Shi et al., and Ueda et al., have cast new light on how polymer chains actually proceed in electrophoretic motion. A representative example of what is seen is shown in the center. The red line represents a labeled polymer chain. The polymer chains are sufficiently extended that their shape can be imaged via video microscopy. At the moment, that red chain has been entangled, is wrapped about the black chain. The red chain is a configuration described as a J configuration. The chain is advancing to the left, the green arrow. The red chain drags the black chain along. The places where the moving chains and the matrix chains intersect have many of the properties assigned in heavy bead models to heavy beads, with one important exception: the beads are free to migrate along the chain, and indeed, as if you had the situation seen here, the electric field would drag out the long end of the red chain and pull the other end of the red chain backwards until it unentangled itself from the invisible in microscopy black chain. The motion, therefore, is motion in which the chain ends move first and the chain center follows. If you had a star polymer, that's seen below, the arms of the star would reach out first, moving to the left. The center would follow behind. This is the motion seen by some, but not all, types of squids, the family of the teuthidae, and therefore we describe this as teuthidic motion, squid-like motion. At high field, there's a dramatic additional change, as observed by Ueda et al. The polymer chain stretches out and advances point first, the I conformation, somewhat like a submarine sailing through a field of huge seaweed. This is also described as reptation, but it should be recognized that in classical reptation, the chain conformations remain the equilibrium random conformations, not the straight line seen here. So the word reptation is being used with a slightly different meaning in this case. Noteworthy in this discussion and these measurements are the transitions that are not being seen. There's a transition concentration in some models, the overlap concentration C star. At low concentration, center of screen, polymer chains are well apart from each other. As the concentration is increased, you have more and more chains in the same space. There's then the transition concentration C star itself, red arrow, and then we get up to the higher concentrations in which the polymer chains are overlapped. To make the separate chains visible, I've colored the chains red, blue, green, black. They're all the same chemical. I've labeled them so that you can see what you're looking at. In the theoretical description associated with the overlap model, an important issue is the notion there are chains, there are holes between the chains, and there is an Ogston model which describes separation as occurring because those holes between the chains have a concentration-dependent size. However, in the Ogston model, you only get separation at concentrations above C star, concentrations at which the polymer solution actually has those holes, such as the one indicated by the black diamond. Furthermore, if you look at the Ogston model, it doesn't really matter how long the chains are as long as they're long enough to form those holes. And therefore, if you ask how does the electrophoretic mobility depend on matrix molecular weight, the answer is that the dependence should be m to the 0. There should be almost no dependence. What is actually found experimentally is quite different. As Barron et al. Demonstrated, you see separation at very low concentrations. The mobility has a concentration dependence that's smooth and continuous through C star. The obvious explanation within the confines of electrophoretic theory at the time was that you had Ogston separation at higher concentrations, and you must have some additional separatory mechanism operative below C star. That was indeed reasonable from the perspective of electrophoretic theory, as we'll see when we get to, for example, the treatment of probe diffusion. The reason that the mu of C is smooth and continuous is fairly clearly that there's only one physical process going on, and it is not Ogston-type sieving. There are transitions that are apparent in experimental measurements. First, the electrophoretic mobility does depend on the probe size. It does so through a stretched exponential for smaller probes, a power law for larger probes, with a sharp transition probe size between them. Note, by the way, the fact that we can say this is a stretched exponential, not a power law, or this is a power law, not a stretched exponential, means that we can tell the two of them apart using our numerical methods. Furthermore, as discussed earlier, we have the appearance of the I configuration. The moving polyelectrolyte chains get stretched out if you run up the electrical field enough. Finally, for moving polymer chains, polyelectrolyte chains, the electrophoretic mobility can depend on electrical field. For weak fields, it doesn't. We're in the linear regime. However, as shown by Mitnick et al., if you run up the electric field enough, you get into a region where the apparent electrophoretic mobility depends on the strength of the electrical field as a power law. You have moved fairly conveniently and directly into a region in which nonlinear dynamics have become important. There is some reason to suppose that these transitions are not entirely different from each other, and we may be looking at different aspects of the same phenomenon. And now we come to the point where electrophoresis actually tells us something very important about polymer motion. The key question is whether we are really in the linear response regime, the low electrical field regime, before we hit things like the I conformation and a mobility that depends on E. If we are, then the arguments of Einstein and his derivation of the diffusion equation apply, and the motion of the polyelectrolyte, the driven motion due to the very weak electrical field, and the diffusive motion of the same chain under the same conditions must use the same drag coefficient and the same mechanisms. That's the fundamental part of linear response theory. What can we conclude from electrophoresis? Polymer motion through polymer matrices is not what is suggested by some models. If we are truly in the linear response regime, we can see immediately that electrophoretic motion is teuthidic, chain ends first, chain center dragging behind. That's equally true for linear chains and for star chains. And therefore, diffusive motion must, due to the linear response theorem, also be teuthidic. That is, the chain ends lead, the chain center drags along whatever chains are encountered. That explains immediately why linear chains and star chains of the same size have very nearly the same electrophoretic mobility, namely they're using the same mechanisms, and fine differences in topology aren't doing anything. That's exactly the opposite of reptation pictures, in which linear chains can reptate, slither like a snake through a matrix, but star chains must use a totally different mechanism for advancing. Well, electrophoresis appears to refute that interpretation. In closing, we showed that there is a systematic phenomenology for how the electrophoretic mobility depends on concentration. It depends on concentration quite systematically as a stretched exponential x minus alpha c to the nu, this stretched exponential, and therefore there are those two parameters, alpha and nu, that both depend on the probe size. Well, how do they depend on probe size? And these two graphs show us for probes in 1 megadalton polyacrylamide. This is again the beautiful data of Barron et al. And I've plotted alpha and separately nu versus probe size. You see alpha ramps up as you make the probes larger. Nu has this funny, actually fairly sharp peak for probes of a particular size and is lower on both sides. And therefore there really is a phenomenology here. Having said that, some readers may be a bit surprised to see that I'm somewhat blandly assuming this is all perfectly reasonable, this is not surprising. If we had done this study and discussion chronologically, starting with probe diffusion and viscosity and tracer diffusion, we would have reached electrophoresis in one of the last chapters in the book, not the first chapters in the book, and you would hear me say this and you would just say, gee, it's the same picture all over again. That's not quite the way I ordered the chapters for what I hope you will agree when we're done with everything were good reasons.